So part of that discussion of those quiz results, we touched on calibration. And Vivek reminded us that at a large scale, calibration is about altering the assumptions in our model to best align emergent model behavior, endogenously produced quantities from the model, things produced by the model, generated by the model, aligning that with observed data, right? We use data in models in many places. And up here, say if these parameter vectors, and that's an important place where we often have data in those parameter vectors. But often we have more data or a large amount of data concerning dynamic phenomena, things we observe in the world that the model's trying to explain or generate or account for. And we can leverage that data using a variety of processes. And the most basic in our toolbox of systems data science is calibration. So we try to we alter our assumptions that are less pinned down about the model so that the model results, the information generated by the model best matches what we observe from the world, right? And there's a lot of details. We'll talk about them briefly. You saw them in the video. But broadly, that's the enterprise to which we press ourselves with calibration. Trying to best match model outputs against observed data from the world. But the truth is, it's broader than that. We're trying to see, and Malcolm gave a nod to this before, we're trying to see the degree to which this hypothesis we have about the world as captured by the model. A model is a dynamic hypothesis. It's a representation in a quantitative form and a precise enough form to be simulated, to be run over time. It's precise enough assumption. By precise, I don't mean accurate necessarily. I mean specific enough that we can run it over time. You can ask, what's the consequence of this hypothesis? That's what a model is. It's a way of capturing our thinking in a precise enough way we can test it. We can test it often against empirical data. So the model represents sort of our, as best we guess, often our thinking about the world. Not always. The models we build for other purposes. But often it's sort of a best guess of what we think might be going on in the world. And by running it, we can see, does the behavior that is implied by that assumption, does it match? Does it accord with? Does it basically have face validity against data from the world? Right? Now, we'd like it to match that data from the world when we don't know, we don't have good assumptions about certain things. Ideally, we'd like it to match it as well as possible. But a really big purpose that calibration serves is to just know, is this hypothesis as represented by the model, is it at all plausible? Does it plausibly accord with what we see from the model, from the world? Remember, I articulated from this room at the beginning of the semester that models are learning vehicles. They're learning tools. They're learning prostheses, as my colleague Jeff McDonald says. The tools for debugging our thinking. And from just about here last time, I further emphasize that point, right? It's not that the model is the truth, but it can speed us towards the truth by helping us figure out when our cherished understanding about what might be going on in the world just doesn't add up. It doesn't produce results consistent with what we see from the world, right? Do you get that point? And that's a lot of the function of calibration. It hurts a bit. Better stop. That's a lot of the goal of calibration. It's just seeing, as we run the model, does it add up? Does it match at all plausibly the observed data from the world? And we'd like to tweak it so we can best match it. But an even bigger signal is, look, it doesn't hold water. It just does not explain this data from the world. And often that's our learning opportunity. A failure in calibration is not a failure of our modeling. It's a success of learning if it's interpreted right. It lets us fail forward. You sometimes hear it, cited these days as fail early, fail often, in an entrepreneurial context. And that's kind of in the spirit with which Francis Bacon in the 1600s said, truth emerges sooner from error than from confusion. Take a stance, try it out. Test it. If you sit back and say, well, I don't know what it is, I don't know what this, this behavior it could be explained by in the world, nothing ventured, nothing gained. You haven't really moved forward. If you posit a model that accounts for and it's invariance with that, it's in space variance with it. It doesn't match it. It doesn't seem at all plausible. The world has these oscillations that your model doesn't accord, or the model has this really behavior where infection concentrates in certain areas geographically your model doesn't account for, despite your attempts. It lets you fail forward. It lets you say, oh, okay, we need something else to account for this. And you can modify your something. You can modify your thinking. You've learned. No. Do you understand that? And that's the bigger enterprise to which the systems data science methods, including calibration, aim. Okay. So it's not just a mechanical process. Okay, time to make the donuts. We alter our assumptions and we best match the data, and we come up with a better match and we're done and that's it. No, there's a learning opportunity. Some of my best learning has been through calibration. And I'll tell you, for those interested in data science, those interested in leveraging this growing richness in this age of big data, that often that learning is not merely about the model, not merely about our dynamic hypothesis, whether it's solid or not, but it's about data from the world. Quite a few times, say 5, maybe 6 times now in my career, I can enumerate them. We've had a model that seemed to make sense. It integrated what we were hearing from experts in that area, our best understanding. We built these models, and sometimes they were agent-based models, sometimes they were stock flow models, what have you. And sometimes hybrid models, and we ran them to test them against data from the world, and they just didn't add up. Maybe they matched most data, most types of data we see from the world, but certain things they just could not accord with. And I remember, for most such occasions, I was feeling a bit sheepish. I was feeling a bit crestfallen or a bit embarrassed, because the model was, I'd been working on this model. The stakeholders were really excited to have this model, and I said, it seems to be behaving pretty reasonably, but it's just not according with this data in this area. And I remember for each of those times, the stakeholder said, oh, don't worry about that data. We changed the definition of what it meant to have X, during those years. So those years you can't match, that was because it was operating with a different definition. And we know the data's weird from that year. So don't worry about it. That's you're comparing apples with oranges for those years. The model shouldn't explain that, because it was based on a change of definition. They changed how gestational diabetes was termed by changing the standard for how centrifuges would be used in the process of measuring the requisite assays in the lab, or how TB was classified. They started to count cases of so-called incipient TB as active TB, even though it wasn't previously or later wouldn't have been counted as active TB. I remember one case. I was young then, and didn't yet have 3 broken ribs, and I was about your age, maybe a bit older. And we had consulting clients that we went to and said, you know, we've really worked on this. We stayed up all night to produce this model, and we said, you know, we just can't match this data in this area. And they said, oh, don't worry, that was for grade 1, that time series. We couldn't match the grade 1 time series. All the others matched fine. I said, look, we started counting as of this year, we started counting kindergarten as part of grade 1. So you can't match it because it was a changed definition, a changed meaning of what was counted and what was not. So what I'm saying is that these processes, and calibration is the most basic of them, for bringing models together with data, teach you not only about the world, they not only debug your thinking in terms of processes, they let you spot things in the data, problems in the data you didn't otherwise know about. They let you spot that this data has something wrong with it. And let me tell you, for those starting out on the road towards, you know, contributing to the growing field of data science, data doesn't come from heaven. You'd be shocked to see how certain data it comes about. See how the sausage factory works. It ain't pretty a lot of the time. And models help us critically evaluate data. They help us test, you know, if there are anomalies in data that would otherwise go unheeded. And if we just took that data and put it into a machine learning algorithm, we wouldn't have learned about that. It was through the models capturing the structure, how elements of the system are believed to work, that we spot those problems. Just putting it into an algorithm that tells you, use this as to classify, you're missing some opportunities for learning. Okay. So calibration is about more than a mechanical process. I did want to give you a glimpse of the mechanical process that is used in the midst of that opportunity. There is a component that's a little bit more manual. And to this end, I'd like you to open up AnyLogix, those who have it. And I want to go in and take a look at an example model. If you go to, and you see the thing, if you go to help example models, it will come up with a sort of a screen here. You may have to make it larger by double clicking on this tab. You can double click it again to make it small again. And I'd like you to scroll down. So how did I get here? I called up AnyLogix. I did help example models. Oh my goodness. Oh, okay. So those remotely secure benefit, but those I'm neglecting those here. Okay. So AnyLogix, you call it up, you go to help, you go to example models, and this screen will come up. If it's really small, you may have to double click on it here. In any case, scroll down, go to SIR agent-based calibration. Okay, and click on that, and it will load it in. Okay, I've already done that ahead of time. Let me close this one so it's not a distraction. Now, SIR agent-based calibration is a built-in model. Okay, it's a built-in model that AnyLogix provides to illustrate in rough terms, elements of the calibration process. And for those who have started on assignment 3, there's actually a problem that builds on this. Now there's 2 experiments in SIR-HMS calibration. One of them is actually more of a sensitivity analysis. If we had time at the end, I might show that, but I really want to focus in on calibration because I've spent a fair bit of the time already talking about sensitivity. So I'd like you to go, I stand corrected. If we double click, so this is an agent-based model. It's an agent-based model of SIR, agent-based model, where infective individuals can spread it to others who are next to them in a, it sends it to random people in the entire population, not just people next to us. Excellent. That would be an interesting, structural sensitivity analysis in a way by changing this to only contact people in the body. But there's an SIR model taking place in a broader population. It's interesting. I hadn't remembered that this built-in model just sends it to a random person. But here we have this infection going on, and the rate of it depends on the contact rate and the infection probability. Okay. Now in the calibration here, and excuse me, there's also a recovery time here, which is average illness duration. Okay. And the idea here is that we have some historic data for that we could use to test this model against which we can test it. And so we have data in particular concerning the number of infectious people over time. And if you want to see that, actually, it's in calibration here. And if we go to calibration, we'll see that over on the left-hand side of calibration experiment, we have this DS thing called dataset infectious historic, okay? And that will be read in from a table function, also visible here, which describes the number of infectious people over time. Okay, here we go. So for different time periods every 2 days, time 2, time 4, time 6, time 8. The idea is we have some empirical data that specifies how many people are in the infectious state at that time. And we want to alter our assumptions about parameters here. Let's go to calibration. We want to alter our assumptions about parameters, specifically parameters, contact rate and infection probability, to best accord with that data. Now, personally, I think it's a little bit silly because those two are just multiplied by each other, and I think it'll be more plausible if we had altered contact rate and average illness duration, but we'll bear with this for now instead of trying to plot this. Okay. The only way in which those two are used, I think, is by dealing with multiplication of them. So that's really the operative parameter. But here we're going to alter assumptions about contact rate and infection probability within these ranges. So for a contact rate, it'll go. We'll examine values for it from 0.5 per day, people that you interact with per day, to 5 people per day. And for interaction probability from 0.1 chance of infection per discordant contact, per contact between infected and susceptible, to 0.8. So the idea is we're going to alter our assumptions about these parameters to best accord with that data that was seen earlier. So the model outputs data that's as close to this as possible. Is that idea pretty clear? Yes.
The step is great, it means that the step is set as default value
Sorry,
in parameter, like the calibration.
oh, yeah. So we'll go back to, thank you for the question. So I think you are referring to like here. Yeah, so in this case, there's no minimum resolution with which it's altering these things. So it may tune the value at very fine levels later in the calibration process. Or it may do so in very coarse levels. There's no kind of fixed size where it examines it with this value and with this value plus some delta, that value plus 2 delta or something like that. It's tuning these, it's kind of honing in on values for contact rate, infection probability per discordant contact, which and it may adjust those at very fine levels or very coarse levels. It's not forcing it in some grid. Yes, Babs.
Oh, I was just saying, so it's like when we talked about continuous and discrete for fixed, the step size is available because there is a step size, continuous sizing.
Correct. Yeah, I think a very good point. Very good point. If this were discrete, we would now have a step size. So discrete means we're examining particular concrete values, this or that or that or that, within some range with a step size. It's like, and what you might imagine exploring a grid, for the discrete, like maybe this is contact rate, right? And this dimension of the grid, right? And maybe this is beta, that probably per discordant contact of infection. And discrete is like we have these, we have a grid here, and we're exploring points on the grid which have different values of contact rate and beta, but only with this resolution. Continuous is it'll vary it, and maybe it gets better and better, and it goes into a value here. Is that clear? Okay. Okay, so let's see this thing in operation. Let's get this show on the road. We're going to run this calibration experiment. And by the way, it's running it 500 times, and running it each time it's a different random number seed, so it has different particulars about who infects whom, right? And it runs 5 times per parameter vector. So it's altering the assumptions about those 2 parameters. You could imagine if it's 3 parameters, you saw this in the video, but if it were 3 parameters, we'd be exploring, like beta, C, and tau, right? Here it's just 2. It's like it's exploring a face of this cube, right? It's altering one and it's altering the other. It's trying to find the best match by exploring the space, the combination of contact rate and beta that yields the best match. Do you get that point? And when I say the best match, I mean the match between the model output and the number of cases that we saw in that historic data, which is shown there. We can't plug this, again, I said it earlier during the pop quiz review, but we can't plug these numbers into a parameter assumption. The model generates the number of infectious cases over time. That's why we build SIR models, right? It generates it over time. And we want the generated values from the model for particular values of contact rate and beta to best match this historic data. Do we get that point? Okay, so let us compute. Okay, so I'm going to, I should tell you, yes, I should tell you, if you want to run along with this, that's great. Just, if you go up to the top of this calibration, make the minimum available memory 1024 megabytes, 1 gigabyte, okay? Because the default one is too small. It's 128 megabytes. It tries to be memory sipping and it can't even run. Okay. So I'm going to run it and we're going to see some results. I'm going to try to explain what's going on here. Okay. So what's going on is that as we run, it's adjusting contact rate and beta. Remember that? But each time, as I said, it's running multiple realizations, multiple times. It's running what AnyLogic calls replication. So here it's running it 5 times for a given assumption about the parameters. So to evaluate how good it is at, this point here, for example, or at this point here, it runs it 5 times. Why does it do that? Because of what? Stochastic, right? Because if we just took it at face value, it may be a fluke. Do you understand that? Yeah. So a given realization might match quite closely to the empirical data, but that doesn't mean that parameter value is really good. It may just be that's within the range of variation. So when we run it, there's some historic data we're trying to map. Current output, this blue, is giving us a sense of sort of the latest time where we and I think that's for a particular realization, if memory serves me. And red is the best so far at matching it. And you'll notice as I run this, initially it started with a very poor match. There was a so-called objective function that it evaluated that measures the discrepancy between what the model's putting out, say the red, and what the historic data is, the yellow. So it needs some way of saying how different are those, how discrepant, how at variance are they, right? If they're right on top of each other, we'd expect the objective value to be 0. If they are quite separated, we'd expect it to be much value, if they're right on top of each other, much slower or much lower. Okay, so we run this, and you'll notice some runs give very high values of this. Some give lower. I believe each of these current objectives is from running 5 times with a certain parameter value. Now, what general pattern do you see? So here we have what's shown here is time and number of infectious people. What's shown here is iteration, successive values of the parameter sets assumed. We're exploring. Each time we explore, we record what was the objective value for that parameter set when we ran it 5 times and took the average. How well, for that assumption of parameters, did it match on average across those 5 realizations? And one thing you see is that they're all over the map, right? Some parameter values give good matches, some don't, but it's learning over time. It's finding assumptions about the parameter that are getting better and better. Initially, it was like over 1,500. And now maybe it was about 1,600. Now it's like 10 times smaller, the subjective value. And it actually will report here what is that contact rate and infection probability that it uses. So this process is called optimization process, right? It's finding, trying to optimize the value of, to assume about data and see such that on average for the 5 runs, it best matches the observed data. And it's getting better and better. But there's diminishing returns, right? It finds, oh, I can do a bit better. Oh, I can do a bit better. But a lot of its original gains were very fast compared to its gains now. But it's doing it. It's honing in. It's got an objective around 100 now, and it's zeroing in. So this gives a little bit of a flavor of the mechanics of a given calibration attempt, right? But I don't want you to lose track of what I emphasized before, which is really calibration is an opportunity to learn. If you just view it as a technical hurdle to get over, a roadblock. You gotta get past to, use the model for real things. You're missing a big opportunity. Modeling is about learning. Calibration tells you to what degree is your model able to account for patterns. These patterns, these ones simultaneously, or is there tensions where it can account for A, B, C, but not D and E? Or you can account for D and E, but not A, B, and you can do pretty well with C. Yes, Malcolm.
So say you have some historical data that's kind of sampled like cases
Yep.
10,000, but
Yep.
you can't run an ABM that supports something like that. How would you?
10,000 people?
Well, I mean, I'm just using.
Or
like a-
good, yeah,
Given limited constraints,
Yeah.
say there's 30 million people
Sure.
in population, you
Sure.
can't do an ABM
Sure.
that big. How can you scale
yeah.
the observations, which might be from a very
Yep.
large population,
Yep.
down to something manageable
Good.
so that it's still legitimate?
So there are formal methods for doing this, okay, for reason about how does an ABM's result scale as you change the population size? Okay, now. There's actually quite tricky aspects of it. As you can imagine, if you start getting down to 10 people, to 100 people, you start getting to quantization error, like going from 10 to 9 could mean the infection never gets, started at all. Just by chance, a lot more. Also networks, become a lot more quantized, if I go from, 1 million population and each people has 100 connections to 10,000 population, each person has 1 connection, that may alter things quite a lot. Also, there are certain measures like prevalence, the fraction of people that are infected that you might think as output might not change much from a large to a small model. But if you use the count of people that are infected right now, it's going to change in proportion to the population. All these things can be accounted for by a theory of dimensional scaling. And just like folks build bridges, small scale versions of bridges, civil engineers traditionally, to reason about how would a bridge behave at scale, if it was going across the Golden Gate, with the Golden Gate across San Francisco, between Sausalito and San Francisco, just as they start with small scale airplanes, small scale versions of bridges, they reason about how that scales up to a full scale bridge, not in a linear way. It's not always linear. Some things may scale up invariantly. Some things may scale up with the square root of the difference in population, some linear to the population. It really matters, and there's a whole theory for this, okay? But it's a very good question, and it has some very good things that can help us address it. But it's a prime question for reasons that Amna was referring to earlier about this whole issue of what modeling type, scales nicely with population size versus, you double the population size, it doubles the runtime. In the agent-based models, you have that big hit you take as you grow population size, and there's ways we can deal with this. Just like engineers deal with the issue, they can't build a full-scale model of the Golden Gate Bridge in their lab here at the University of Saskatchewan. As cool as that would be. Right. Okay. So that's all we have time for today. Hope that's helpful. I'm going to be assigning for next week something on discrete event simulation more. We might do one lecture on a modeling frontiers topic before we end the course. Okay. Thank you, everyone.